Okay, everyone, we're going to get started on our 6.5 concepts review. This one is about the trapezoidal method, so hope you'll join us for this. Let's get started. So it looks like I have to determine and evaluate a definite integral for 1/40th 0 cubed 2 times 0.05 cubed, etc., etc. And as I look at that, that's kind of already set up for the trapezoidal rule. Let's take a look at what I mean. So if you take a look at this, this is right here would be f of 0, 2 times f of 0.05, 2 times f of 0.1, all the way to f of 2. So this is already set up, and it looks as though f of x is x cubed. So when I put this together and I take a look at that, I get, of course, that's kind of what we were talking about. And f of x really does look like it's x cubed, and it looks like a is equal to 0, and b is, I know that says 0, but it should be 2. We'll fix that in a second. So that's going to be equivalent to that antiderivative, or the integral of x cubed from 0 to 2. And when you integrate that, no big deal. That's just 1/4 x to the 4th from 0 to 2. And then when you substitute your limits, you get yourself a 4. So that covers that. That integral is going to be 4. Now the other part of that question is which one is bigger? And when I look at that, the x cubed function is concave up. And if you draw yourself a concave up function, I'll go ahead and do one roughly over here. If you draw a concave up function, and then you put a trapezoid on it, you're going to see that your trapezoid is going to over-approximate your concave up function. So this is an over-approximation of what that integral would be, or the trapezoidal sum would be an over-approximation. We would expect that trapezoidal sum to be greater than 4, basically. Taking a look at question 2, this is even a little bit more mysterious, because now we don't have this in function notation, but we do know it's a trapezoidal approximation. So let's see what that trapezoidal approximation looks like. Well, the first thing I want to say is you have the 1/2 in the front here, and if you're talking about a trapezoidal approximation, that 1/2 should be 1/2 of delta x, implying that delta x here is going to be equal to 1. What else can we figure out? Well, from the sum, the first term is 0.5. The second term, or the second y coordinate, would be half of that 1.5. Remember that 1.5 is 2 times the second y coordinate, which tells me that the next one is going to be 0.75. Similarly, the one after that's going to be half of 2, which is 1, and then half of 2.5. Half of 2.5 is, of course, 1.25, etc., etc. Now, taking a look at how these are related, this looks linear to me, because to get from 0.5 to 0.75, which would be the very next y value, you're adding 0.25. And then to get from 0.75 to 1, you would add 0.25 again. And then to get from 1 to 1.25, you would again add 1.25. So I don't know what the function is per se, but I do know it's going to be a linear function, because the y coordinates are all, or if the x coordinates are evaluated every 1 unit, the y coordinates increase by 1, or when the x coordinates increase by 1, the y coordinates increase by 0.25. So this is a linear relationship with the slope equal to 0.25. And then if I take a look at the leftmost point and then the rightmost point, the leftmost point is 0.5 and the rightmost point is 5. So when you draw that out, you're looking at a trapezoid. Let's kind of draw that out for you. We're looking at a shape that's kind of like this. Okay, it's a trapezoid. The base on the left here is 0.5, and then the base on the right side here, that's 5. And now the real trick is, how long is this trapezoid? How long is it from A to B? If you count it out, it would take you, well, if f of 0 is 0.5, and then f of 1 would be 0.75, and f of 2 would be 1, and f of 3 would be 1.25, you would get to 5 when you get to f of 18. Now, you're starting at 0, but it doesn't really matter where you started. If you started counting at 2, for example, you would get to 5 at f of 20. So because this is a trapezoid, the area of it is preserved as you shift it from left to right. So we'll just use 0 to 18 as our trapezoid because it's really convenient. So we got our integral of f of x. That's equal to the area of a trapezoid, 1/2 base 1 plus base 2 times the height. Now we can substitute our numbers. On the left side, we know that the height is 0.5, and on the right side, the height is 5. And as we stated already, our x-coordinates, our minimum x-coordinate is 0, and our max coordinate is 18. And if it's not 0 and 18, then it's 2 and 20, or heck, negative 5 and 8, I think that would do it. However many it is, it's going to be 18 units across the base of that trapezoid. So now you have something which you can evaluate, and you get yourself 49.5. So this is our trapezoidal sum. It's very tricky. I think this is a tricky question because you really need to figure out exactly what that function was, and it's not quite obvious all the time. And which one is greater, the integral or the trapezoidal approximation? And actually, in this case, they're both equal to each other since the shape is a trapezoid. So trapezoidal approximation is equal to the trapezoid. Imagine that. Question 3, you're going to skip because this is Simpson's rule, and that's actually not in our curriculum. Other fine calculus teachers might want to teach that to you, but we're not going to do that in our class. And then finally finishing up with our question 4. For strictly increasing positive valued function, explain why the average of the sums of the inscribed and circumscribed rectangles, all of constant width, is a trapezoidal approximation. For a strictly decreasing function over an interval, a similar conclusion can be made. Okay, well, let's take a look at, first of all, the inscribed sum. So the inscribed sum, over here, here's our inscribed sum. You notice how you evaluate right at the very left side of this. We should probably zoom in. Right at the very left of that, you can see f of a being evaluated. And on the right side of this, you notice that f of b isn't evaluated. Instead, you're evaluating f of b minus your delta x. So for our inscribed sum, we have this really nice equation. You got delta x factored out of everything. So delta x times a quantity of f of a plus delta x plus f of a and 2 delta x's, all the way to f of b minus the delta x. Now the circumscribed sum is going to work really similarly. Notice that for the circumscribed sum, we're not evaluating at a, we're evaluating here at a plus delta x, and then a plus 2 delta x, and then a plus 3 delta x. Remember, the far left side is a, and then the next one is a plus delta x, a plus 2 delta x, etc. Notice that on the right side, we're evaluating f of b. So we're evaluating from f of a plus delta x to f of b. So if you see what we have here, we have our delta x evaluated at, or delta x multiplied by our function evaluated at a plus delta x, a plus 2 delta x, etc., all the way to f of b. And now for the fun part. We're going to find the average of these two. So how do you find an average? Well, you add those two concepts together and divide by 2. I know, I feel like I always say that calculus and average is always going to be an integral, but that's not really the point here. We're trying to figure out, in this case, average in terms of, basically an arithmetic sum. Here's our average. We're adding the two together. This one right here, let me see if I can highlight that for you. This part right here is, this part is the inscribed sum, and then this part down over here is the circumscribed sum. So we're just adding them together and we're dividing by 2. Now a few things happen as you add these two together. Notice that you can factor out a delta x from both of these, and when you do so, you're just adding every term in here. I've highlighted a few things on purpose, color keyed. Notice how the a plus delta x is in here. This is in this average twice. Same with f of a plus 2 delta x, f of b minus 2 delta x, f of b minus delta x. F of a and f of b, they're only in that sum one time, so we don't have to evaluate them more than once. So when you put it all together, you get this lovely sum over here. Notice you have 2 times f of a plus delta a, 2 times f of a plus 2 delta a. Basically, all the interior terms of this sum are multiplied by 2, and the exterior terms, f of a and f of b, those are only multiplied once, mainly because f of a and f of b, f of a only occurs in the inscribed sum, and f of b only occurred in the circumscribed sum. And take a look at what that is. That is the trapezoidal formula. So here we have kind of proven that the trapezoidal sum is just the area, or it's just the inscribed sum and the circumscribed sum averaged out. So that's it, everyone. I hope you enjoyed that. This was actually not that difficult. Kind of fun, actually, taking a look at the trapezoidal sums. And I'll see you next time. Bye.